Nearly 1,000 feet below these footsteps is the floor of a canyon. And between the people walking here and that drop is a transparent glass deck. But the glass is not what keeps this bridge suspended in the sky. The span is roughly 430 meters from cliff to cliff. The cables have to transfer enormous forces back into the canyon edges, and the completed bridge has to remain comfortable under both wind and moving crowds, all while appearing light enough that the landscape remains the main thing visitors see. Then there is the question almost everyone eventually asks. What happens if the glass is damaged? Before people could walk across this bridge, engineers had to build the suspended structure beneath the glass, control its movement, install dozens of transparent panels, and prove that the walking surface could carry the loads expected of it. So, how do you build something that looks almost weightless across a canyon this deep, and make hundreds of people willing to step onto it? The answer begins long before the glass. Zhangjiajie Grand Canyon, in China's Hunan province, is a landscape of steep forested slopes, exposed rock and dramatic vertical relief. To connect opposite sides of this canyon, the bridge would need a main suspension span of roughly 430 meters, or about 1,410 feet. The walkway would be only about 6 meters wide, and roughly 300 meters, almost 1,000 feet, would separate it from the canyon floor below. For the designers, simply crossing the gap was not enough. A massive, visually heavy bridge could have overwhelmed the landscape. But this crossing was intended to preserve the sensation of standing almost directly above the canyon. The finished bridge therefore had to look unusually light. That created an immediate contradiction. A bridge can look thin. It cannot behave as though it has no structure. It still has to carry its own weight, the walking surface, hundreds of visitors, changing wind loads, and the dynamic forces produced as people move across it. The solution was an earth-anchored suspension bridge with an unusual spatial cable arrangement. And the easiest way to understand the bridge is to follow the loads. The glass panels carry the local loads beneath a visitor's feet into the supporting deck system. From there, the suspended steel structure, hangars, main cables, and anchorages carry the bridge across the canyon. The main cables work primarily in tension. But those cables cannot simply stop at the cliffs. The enormous forces they carry have to be transferred into substantial end structures and ultimately into the ground. So while the transparent floor is the part visitors notice first, the bridge depends on an entire structural hierarchy around it. And that meant the first major construction problem was not glass. It was the canyon itself. Before the suspended span could exist, engineers had to establish the systems at both ends that would eventually carry forces from the bridge into the surrounding ground and rock. Surveying and alignment were critical. Two construction zones separated by hundreds of meters of empty air had to become parts of one continuous structure. At the canyon edges, anchorage and foundation work had to be carried out in extremely sensitive terrain. Some of this excavation was completed without blasting, reducing disturbance to the surrounding scenic environment. But even after those end structures were ready, there was still nothing between them. No deck, no walkway, no place for ordinary cranes to stand beneath most of the span. That is where the logic of suspension bridge construction becomes especially important. Instead of supporting the bridge continuously from the canyon floor, the project had to create a system that could carry construction out over the void. As the suspension system was established, temporary access and cable-based construction equipment could begin operating above the canyon. For the crews working there, the construction site was no longer a platform on the ground. It was a temporary catwalk hundreds of meters above the valley below. Fall protection, lifelines, and carefully controlled access were not optional details. They were part of working in a place where one side of the job site was effectively empty air. The main suspension cables gradually established the long, curved geometry of the bridge. Below them, hangars would connect the suspended deck to those cables. But cables alone still did not create a usable crossing. The bridge also needed a stiffening structure. Technical descriptions identify a stiffening box girder system extending for roughly 373 meters. That structure is one of the most important parts of the bridge that a visitor may barely notice. A suspension cable is extremely efficient at carrying tension. But a long pedestrian deck cannot simply behave like a loose walkway hanging between cables. Wind, uneven loading, and moving crowds can all change the forces acting on it. The stiffening system helps control the shape and movement of the suspended deck while distributing loads along the span. From above, the finished crossing appears remarkably light. Move beneath the glass, and the hidden engineering becomes easier to understand. The transparent panels sit within a supported deck. That deck is part of a steel stiffening system. The steel is connected through hangers to the main cables, and those cables return their forces to the canyon edges. The bridge looks simple only because most of that load path stays visually secondary. Building that suspended steel structure across the canyon was one of the most difficult parts of the project. The stiffening girder was divided into 37 sections. Instead of constructing the entire deck from one side, sections were erected from both ends and advanced toward the middle of the span. A cable crane was used to move heavy girder sections out above the canyon. Each piece had to travel into position while suspended high above the valley. Then it had to be lowered and connected to a structure that was itself already hanging from the cable system. This was not a process where the geometry stayed perfectly fixed from beginning to end. Every new girder section added weight. That changed the forces in the suspended system. And as the suspended deck grew, the geometry of the cables and the position of the structure continued to evolve. So engineers could not simply measure the unfinished bridge once and assume every future section would arrive at exactly the same coordinates. They had to track the changing shape of the structure as erection progressed. One segment, then another, from one cliff, then from the other. Gradually, the empty canyon became occupied by steel. The gap in the middle became smaller. 36 sections could bring the bridge almost all the way across. But almost was not enough. One final section still had to fit between the two advancing sides. On December 3, 2015, the bridge reached its structural closure. The final stiffening girder section weighed about 41 metric tons. 41 tons is substantial on the ground. Here, that final piece had to be positioned hundreds of meters above the canyon floor. Its connections had to line up with a suspended structure whose geometry had been changing throughout erection. The remaining opening had to match the incoming steel, and the final section had to become part of one continuous structural system. Slowly, the last piece was brought into position. The ends aligned. The connections were completed, and for the first time, the steel deck formed a continuous crossing from one side of the canyon to the other. The gap was closed. But a continuous bridge is not automatically a comfortable bridge, and on a long pedestrian suspension span, movement matters. Wind was one concern. A narrow suspended deck is directly exposed to moving air, and the structure has to respond without developing motion that becomes unacceptable for the people using it. But the wind was not the only thing that could move this bridge. The people walking across it could do that too. Every footstep creates a small dynamic force. One person is insignificant compared with the bridge as a whole. Hundreds of people can be different. If many pedestrians begin walking at similar rhythms, repeated forces can interact with the natural vibration characteristics of the structure. That does not mean the bridge is on the verge of structural failure. The concern is also about serviceability and comfort. A bridge can remain structurally safe while still moving enough to make people uncomfortable. And on a transparent walkway with almost 1,000 feet of open space below, even modest movement can feel far more dramatic than it would on an ordinary sidewalk. The project therefore incorporated measures to limit vibration and reduce the possibility of large groups developing a highly regular walking rhythm. One of the most unusual features was a series of 72 glass spheres positioned irregularly along the bridge. Each reportedly weighed roughly 750 kilograms. They were visually distinctive, But they were not simply decoration. Their irregular placement interrupted the path pedestrians would otherwise follow. Instead of hundreds of people moving in clean, repeating lines, visitors naturally had to change direction and walk around the obstacles. That helped disrupt synchronized pedestrian movement. The designers also incorporated additional vibration control measures into the bridge. Only after these larger structural questions had been addressed could the feature that made the bridge internationally famous become the focus: the transparent floor. The completed walkway uses 99 glass panels, but these are not ordinary single sheets of household glass. Project information describes a 3-layer laminated tempered anti-slip glass system with a total thickness of roughly 48.6 millimeters, or about 1.9 inches. The key idea is redundancy. Instead of relying on one ordinary brittle pane, the walking surface uses multiple laminated layers designed as a deck system. And because people would actually walk directly on it, the surface also had to provide usable traction. Each panel then had to be installed into the supporting deck with controlled handling and precise alignment. A transparent panel may look visually simple once it is in place. Its support conditions are not simple. The panel has to sit correctly within the deck system. Loads from pedestrians have to transfer into the surrounding support structure. The interfaces around the panel have to be coordinated. And the finished surface has to remain functional while still allowing visitors to look directly into the canyon below. Panel by panel, the steel crossing was transformed. What had been a suspended structural frame gradually became a transparent pedestrian walkway. And this is where perception becomes almost as important as engineering. A steel deck tells your brain that something solid is beneath you. Transparent glass removes that visual reassurance. The structural support has not disappeared, but the view makes it feel as though it has. That leads directly to the question that makes this bridge so psychologically difficult to cross. What if the glass is damaged? A damaged panel would still require immediate inspection and management, but it is important to separate a local deck problem from the global suspension system carrying the bridge across the canyon. The glass panels form the walking surface. They are not one continuous sheet stretching from cliff to cliff. And they are not the main cables carrying the entire span. That distinction matters. A local problem with one part of the deck and a global failure of the suspension bridge are not the same event. But engineers could not rely on explanation alone. The glass system had to be tested. Before final installation, candidate glass systems were subjected to aggressive load-bearing tests. These included truck rolling and heavy stacked cement loads. The purpose was not simply to produce dramatic images. A controlled test allows engineers to observe how a panel and its supporting arrangement behave under known loads. Deformation can be measured, damage can be inspected, and the results can be compared with the performance expected from the design. This kind of testing is especially important for a walking surface that will be used in a way that feels unfamiliar to almost everyone stepping onto it. For the public, the question is emotional. Would you trust the glass? For engineers, the question is different. How does the complete panel system behave under the required loading conditions? By the time the bridge approached operation, the canyon had been transformed. Where there had once been nothing between the two sides, there was now a complete suspended structural system. Main cables crossed the gap. Hangers carried the deck. The stiffening girder connected the span. 99 transparent panels formed the walking surface. And vibration control measures helped manage how the crossing behaved under wind and moving pedestrians. Major construction had begun in the second half of 2014. The steel structure reached closure in December 2015, and on August 20, 2016, the bridge began trial operation. Now the test loads were replaced by something less predictable: people. The design allowed for up to about 800 visitors on the bridge at one time. Some walked directly onto the transparent surface. Others slowed when they reached the first clear panel. Some looked down. Some avoided looking down at all. Their reactions were different. The structural system did not see fear. It sees
Noted.
forces.
Initiating load test.
Weight from
Monitor
each
pressure
visitor
readings.
enters the walking
Readings are
surface. The supporting deck distributes those loads. The suspended steel structure and hangers transfer them into the cable system. The main cables carry tension toward the ends of the span, and the anchorage system transfers those forces into the ground. At the
Load
same
is stable.
time, the stiffening structure
Noting
and
the
vibration
deflection.
control measures help
Continuing the
manage the
observation
movement of the
period.
crossing. That is why the finished bridge is so deceptive. A visitor looks through the floor and sees almost nothing between their shoes and the canyon. An engineer sees the opposite: a laminated glass
Structure
panel,
integrity
a
confirmed.
supported deck, a stiffening structure,
finalize the
hangers, main cables, anchorages, rock. The glass creates the fear. The engineering makes the crossing possible. The achievement was not simply putting transparent panels almost 1,000 feet above a canyon. It was creating a suspension bridge light enough to preserve the view, controlled enough for pedestrians to use, and precise enough to turn 37 suspended steel sections and 99 glass panels into one continuous crossing. The bridge looks frightening because it allows the landscape beneath it to remain visible. But what makes that experience possible is everything the glass allows you to forget is there.